Hello, guys. Welcome to Ramta Solutions. Welcome to your grade 12 Physical Sciences Chemical Equilibrium series. Today, we are looking at the equilibrium constant. So, without any waste of time, what is the equilibrium constant? This is the ratio of the concentration of products to the concentration of reactant. And that we're going to write it for you. So we say it is the ratio of the concentration of products to the concentration of reactants, right? To the concentration of reactants. Okay. Now, now, okay, let's see. Okay, this is better. All right, now we say Kc is equal to, I'm using these square brackets intentionally, product over reactant, right? So now let's say now for a balanced chemical equation, and for a balanced equation, and I'm gonna say a reversible reaction. Okay, so we're gonna say let's say A, substance A reacting with substance B, reaction being reversible, giving us substance C and substance D. How do we get Kc for this reaction? We're gonna say concentration of substance C to the power of its coefficient multiplied by the concentration of substance D to the power its coefficient on a balanced equation, all over concentration of substance A to the power its coefficient on a balanced equation multiplied by concentration of substance B to the power of its coefficient in a balanced equation, right? So these square brackets, they represent concentration, right? They represent concentration, right? Concentrations of aqueous and gaseous substances, okay? Gaseous, aqueous and gaseous substances, okay? So remember, the units for you guys, it is mole per cubic decimeter. For you guys in grade 12, it's mole per cubic decimeter. Okay, but otherwise we work with mole per cubic decimeter. However, for grade 12 or for high school, you work with mole per cubic decimeter. Okay, so these are concentration, equilibrium concentrations. I think I should make it clear that it is equilibrium concentrations of aqueous and gaseous substances. Okay, so we ignore concentrations of um, solids, and of course solids do not have concentration, and we also ignore concentrations of liquids. The reason is not for grade 12, but I will see in future if I can post one of the reasons why you don't include the concentrations for liquids and stuff. Okay, I will post them later. Okay, all right. So remember, I said, guys, these concentrations are the concentrations of aqueous and gaseous substances only. I think I should add that only. That only is important. Okay? So another thing you need to know is that Kc is unitless. Okay, Kc is unitless. Again, the reason is not part of your syllabus. It is advanced. You will learn more about it next year if you're doing science, and maybe if you're studying engineering and also health sciences, because you will learn about rate laws and thermodynamics. Okay, but for now, I'm not going to tell you why it is unitless. Okay, I might do a video later where some of the questions I answer them. Okay, but for now, for this video, let's just take it that Kc is unitless. Okay, Kc is unitless. So remember, this one is for aqueous and gaseous substances only. Okay, these are equilibrium concentrations of aqueous and gaseous substances only. Okay, so now let's now talk about the meaning of the values of Kc. Okay, let's now talk about the meaning of the values of Kc. So, meaning of Kc values. So, this is equilibrium constant with respect to concentration. Okay, so Kc can be when it's greater than 0 but less than 1. What is happening here? Here we are saying reverse reaction is favored. Okay, reverse reaction is favored. Okay, and what does it mean? That means equilibrium is shifting to the left. All right, equilibrium shifts to the left. Okay, now what is happening here? This means we are forming more reactants. Okay, you are forming more reactants. Okay, forming more reactants than products. Then you can also have a situation where, another situation rather, is that when Kc is greater than 1, with this one, the forward reaction is favored. Okay, with this one, the forward reaction is favored. Okay, with this one, the forward reaction is favored. Okay, now what does it mean for us if the forward reaction is favored? This means equilibrium is moving to the right. Right? Equilibrium shifts to the right. So what is happening here? More products formed. Alright? So here more products are formed. Okay? This means more products are formed. Okay? So how do we determine the value of Kc? How to determine the value of Kc? Remember, guys, here is just for classroom purposes, okay? But of course, everything is done experimentally. How to determine the values of Kc? Or the value of Kc. Let me not say values, value of Kc. Remember, I said to you, everything is done experimentally. But for you, you may one, using equilibrium concentrations or amounts, okay, or two, using the RICEE table. The RICEE table. So this RICEE table is R for reaction, initial mole, and then change in mole, equilibrium mole. So equilibrium mole, and equilibrium concentration. Okay, and equilibrium, and equilibrium concentration. Okay, and equilibrium concentration. Okay, and equilibrium concentration. So let me just explain here. Using the RICEE table, the R representing the reaction, I representing initial mole, C representing the change in mole, the first E representing equilibrium mole, and the second E representing equilibrium concentration. Okay. So this is how you can determine your value of Kc. Right? So now under RICEE table, note the following. You need to know this, that initial mole, okay, initial mole plus change in mole, okay, is equal to equilibrium mole, okay, is equal to equilibrium mole. So highlight this, it's very key. Okay, highlight this, it's very key. You will use this equation quite a lot. It's not really an equation that's standard, but just use it so it's easier for you to, to calculate your amount when you use the RICEE table. Okay, so now we are going to begin with examples. Okay, we are going to begin with examples. But before that, let's now talk about factors affecting the value of Kc. Factors affecting the value of Kc. What this means is, what can change the value of Kc? Only temperature can. Okay, it is only temperature. Of all factors affecting equilibrium, none except temperature will change the value of Kc. Now, what does this mean? This this means Kc is a function of temperature, meaning it changes with temperature. Okay, it's dependent on temperature of the system. At different temperatures, your equation or your reaction will have different Kc. Okay, it will have different Kc. You guys got it? Perfect. So these are all that you need. Okay, these are all that you need. Okay, so remember what I said to you. I said the value of Kc is only affected by temperature. Nothing else affects the value of Kc. Okay, now I thought this video would be very long. I don't think so. But hold on. We will be having worked examples. It might be longer than I anticipated, or maybe shorter. Okay, so now let's see. We will have, let me see, we're gonna try 4 examples, guys. Okay, we're gonna try 4 examples. Okay, so example one, let's see. Example one, we are given N2O4 gaseous at equilibrium, giving us NO2 gaseous. Now let's see, the equations are balanced. So now this says a sealed tube contains NO2 and N2O4. Equilibrium is reached at 100 degrees Celsius. The concentrations at this stage. Which stage? equilibrium stage are 0,00140 mole per cubic decimeter N2O4 and 0,0172 mole per cubic decimeter for NO2. Now, calculate the Kc. Calculate the equilibrium constant. Okay, calculate the equilibrium constant. Now you can see this is our balanced chemical equation, right? It is balanced. We can see the substances are all gaseous. And by the way, this is a homogeneous equilibrium because all substances are in one phase. Now let's find our solution. Remember, we had N2O4 gaseous in gaseous phase to 2NO2 gaseous phase. So Kc will be concentration of NO2. What is its coefficient? It's 2 over concentration of N2O4. What is its coefficient? 1. So we are sorted. Now, what was the concentration of NO2? It was 0,0172. So it's 0,0172 mole per cubic decimeter. All right. And what is the concentration of N2O2? It was 0.00140. 0.00140. Okay. Now, let's take out our calculators and confirm this. Let's see. So this is 0,0172 squared over 0,0014. What do we get? We get 0,21. Remember, this is unitless, 0,21. Now, look at this value. This value here is greater than 0 but less than 1. So this means equilibrium shifts to the left. All right? For this one, equilibrium shifts to the left. Isn't it? Equilibrium shifts to the left, meaning more reactants are forming than products. Okay? Great. Now, let's try the second example. The second example has carbon monoxide gaseous phase plus 2 hydrogen gases. I said gases, obviously, gaseous phase. Then forming methanol. Right? So, let's see now what's happening here. So, with this, we will say an equilibrium mixture. Let me say an equilibrium mixture at 500 Kelvin found that the concentrations, found that the concentrations of methanol CH3OH is 0.0203 mole per cubic decimeter. Carbon monoxide is 0 point what? 0 point, oh, 0.085, 0.085, 0.085 mole per cubic decimeter, and hydrogen gas is 0.151 mole per cubic decimeter, right? Is that right? Yes. Now determine the value of Kc. Determine the equilibrium constant. So with this one, as you can see, we have the amount at equilibrium. We don't have to use the RICEE table, right? We don't have to use the RICEE table. Okay, we don't have to use the RICEE table. So let's get our solution. So now, in order for us to get Kc, we need to remember what the reaction looked like. The product was methanol CH3OH. So concentration of CH3OH at equilibrium, its coefficient was 1. So the power is 1. We also had carbon monoxide. Its coefficient was 1. I remember we had hydrogen gas. Its coefficient was 2. Let me confirm. Yes. Yes, indeed. Yes, indeed. Perfect. So the concentration of ammonia is 0.0203. Not ammonia, methanol. 0.0203, while the concentration of carbon monoxide was 0.085, 0.085, and that of hydrogen gas was 0.151. Right? Remember, the coefficient of hydrogen gas is 2, so it's squared. Let's see now. Using our calculators, 0.0203 over 0.085 times 0.151 squared. What do we get? We are getting, correct to 2 decimal places, we are getting 10.47, isn't it? 10.47. 10.47. So what is happening here with regard to the equilibrium position? You can see that it is shifting to the right, right? Because it's greater than 1. Equilibrium is, okay, equilibrium is shifting to the right. So this means the forward reaction is favored, right? So it means in this case, the forward reaction is favored. Okay, perfect. So this is great. Now, I'm going to do the next example that I'm going to do will be the RICE, using the RICE table. Okay, I want you guys to pay attention. So now, I need to go to the next page. So example 3. So I'm deciding to make 3 examples only. So let's see. So this one says carbon dioxide gas reacts with solid carbon according to the following reaction. According to the following balanced equation. And that equation is CO2 gaseous, carbon solid, equilibrium or reversible reaction, 2 carbon monoxide gas. Now, the system reaches equilibrium at 100 degrees Celsius. Initially, 2.38 moles of carbon dioxide was reacted with excess carbon in a sealed flask of 250 cubic centimeter. Proceeding, the equilibrium mixture was found to contain the equilibrium mixture was found to contain 1.90 moles of carbon dioxide. Determine the value of Kc at this temperature. Determine the value of Kc at this temperature. Now, this is nice. Let me see. Okay, I have enough space. Okay, so for our solution, it's important that you note here that initially we are given 2.38 moles of substance, carbon dioxide. Also note that the volume given is in cubic centimeter, which is not what you use. You must convert it to deci. So from centi to deci, what do? You divide by 100, but because it's cubic, you divide by 1000. So it will become 0.25 cubic decimeter. Now the RICEE table. Now check it out. Remember our reaction was carbon dioxide gas plus solid carbon, not copper, solid carbon, giving you 2 carbon monoxide gas. So you will say your reaction, you will then say initial mole, change in mole, equilibrium mole, and then equilibrium concentration. And then equilibrium concentration. Let me just do this. Equilibrium concentration. So I need you guys to pay attention here. Okay, I need you guys to pay attention here. It's very important that you pay attention. So this is the RICEE table. Okay, now let's look at our reaction. We have coefficient of carbon dioxide is 1. So let me just say 1 carbon dioxide, 1 copper, it's solid by the way, and then 2 carbon monoxide gases. Now, initially you are given 2.38 moles. So, but before that, I needed to note something. Reactants will have a negative change. So use a pencil. When you come to this point, please use a pencil. Receiving myself, I'm using a pencil here. Kevin, myself, I'm using a pencil here. Let me see. Okay, perfect. I'm using a pencil here. So the coefficient here is 1. So please represent it as negative 1x because it's a reactant. And here, because it's a solid, you don't have to worry about it. Put dashes all together. And here, it's a product. Since it's a product, use a positive, meaning a plus. Now, what is the coefficient? It's 2. So make it become 2x's. Okay. Remember these. Remember these x's. I write them in a pencil so you can erase them later. Okay. Now, initially you are given 2,38 moles. This is what you have. 2,38 moles. Maybe I should change the color. Let me change the color here. Yeah, I'm gonna use this green. So initially you have 2,38 moles of carbon dioxide. You don't have the product when you start your reaction. So this is what we are assuming. We're starting our reaction, we don't have our product. Okay. So, and then they said to us at equilibrium, let's see, they said to us at equilibrium, 1.90 moles of carbon dioxide was found. So we have equilibrium mole of carbon dioxide. So we're going to put 1.90. Do you guys see that? Now, remember I said to you, you will say initial plus change will be equilibrium. Let me go back to that particular portion in our notes. Okay, let me go to that particular portion in our notes. So to remind you, do you see that? Initial plus change equals equilibrium. Can you guys see that? Perfect. Now we are using it. Let's see now. So how do we use this? We say, okay, 2,38 minus x equals 1.90, isn't it? So what is that? 2.38 minus 1.90 equals x. So what is x? X is 0.48, isn't it? X is 0.48, isn't it? So now this is what we're going to do using a pencil. So now I'm writing in pen. Your x, a single x, is just negative 0.4. Is it negative 0.48? I'm not sure, guys. Negative 0.48. Yes, negative 0.48. Now, for this one here, you have two x's. All right? You have two x's. So this means 2 times 0.48. What is it? It's 0.96. So it's going to be plus 0.96. Okay. It's going to be plus 0.96. Once again, 0 plus 0.96. What is the equilibrium mole? It is 0.96. You recall the container of the volume of your container is 0.25 cubes. So now concentration, you know that concentration is number of moles over volume, right? So what does it mean? It means here you will be saying equilibrium mole over volume. All right? Tell me what you're getting now. So you're getting 1.90 divided by 0.25. What is this? 7.6. So this is 7.6. Again, 0.96 divided by 0.25 will be 3.84 moles per cubic decimeter. Right? Now, what do we need to do now? What we need to do now is to calculate the value of Kc. Right? So the value of Kc here, maybe I can write it here. I'm going back to my black color. Remember, guys, this rough work is also needed for your submission as well. Okay, so the value of Kc, if I recall, it'll be, let's go back, it'll be carbon monoxide. How many? We had coefficient 2. So carbon monoxide to the power 2 all over carbon dioxide, the coefficient was 1. Remember, the copper is solid. We don't include it in the equilibrium constant calculation. All right. So what is this? Carbon monoxide concentration at equilibrium is 3.84. Remember the square. And then what was the concentration of carbon dioxide at equilibrium? It was 7.6. Now, let's see what our value of Kc is. 3.84 squared over 7.6. What do we get? We get 1.94. So our equilibrium constant is 1.94. As you can see, this is greater than 1. So it means you are forming products, more products than reactants. Even though it's slightly above 1, but you're not forming reactants. You are forming slightly more products than reactants. Okay, so this is how you use your equilibrium constant. I wanted to give you 4 examples, but I'm content with this one here. Okay, I'm content with this one that we did here. The rest you will see them when we tackle past examination papers. So this is it, guys. I hope you have enjoyed this. But a part of me says I should also give you the last one because I'm not content with the fact that it had a solid. But if you listen to me carefully, you will recall I said the solid parts and the liquid parts will not be included in the Kc, but the gaseous substances and the aqueous substances will be included. So it shouldn't be difficult. Whatever question you may get, it'll be right for you. Okay, so maybe it's okay to leave it here. So with that being said, it's a wrap and see you next time. The next video will be equilibrium graphs and it'll be concentration versus time. So the last one will be rate versus time. Okay, so let's meet when we look at equilibrium graphs. So with that being said, it's a wrap and bye-bye.